the Digital Marketing Specialist for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter or panelists. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read those questions out during the Q&A segment at the end of the webinar. All webinar attendees are eligible to receive one NETA CTD and one PDH or 0.1 CEU just for attending today. You will receive this in an email within about 2 business days after the webinar. And that email will also include a copy of the PowerPoint presentation and a link to a video recording of the webinar if you'd like to watch it again or want to share it with your colleagues. Remember, you can ask questions at any time during the presentation, and they will be answered at the end of the webinar during the Q&A session. Our presenter today is Dinesh Shajir from the Megger Technical Support Group. Also, to assist with the question and answer session, we'll have a couple panelists joining us today. Robert Foster is a Megger application engineer, and then we also have Diego Robolino as a Megger principal engineer. Okay, let's go ahead and get started. Thank you for joining us today, Dinesh.
Good morning, everyone. My name is Dinesh Shajir. I'm part of the Megger Technical Support Group based out of Dallas, Texas. And today's presentation is on field testing of transformers for winding condition assessment. Transformer is one of the most critical assets in a substation or in a power system. When we talk about transformer, it has various different components that need to be tested and evaluated on a periodic basis to ensure the transformer would work as intended. Components such as windings, insulation, core, tap changer, bushings, insulating oil, they need to be periodically tested, and if there is any issue or problem, preventive actions need to be taken before it's too late. For this webinar presentation, our focus would mostly be on windings and tap changer. There are a number of different field tests that are recommended in various different standards. IEEE, IEC, NETA are different standards where you can get more information about these tests. And each of these tests is testing electrically a certain component of a transformer. For instance, if you want to evaluate the condition of insulation, you would perform insulation resistance and power factor testing. Likewise, if you want to check the condition of the core, you would perform tests like excitation current, core ground, those kind of tests. When it comes to winding assessment, transformer turns ratio and winding resistance are two very common tests that are being performed. And in this presentation, we would be talking in detail and in depth about those two tests. In addition to that, there are some advanced tests that you can perform like sweep frequency response analysis, dielectric frequency response to determine things such as if there is any kind of mechanical movement inside the transformer, that would be your SFRA test. And then you have a dielectric frequency response test that would estimate the moisture present in the paper insulation. There are a number of IEEE standards that recommend turns ratio and winding resistance test. One of those standards is IEEE C571290, and this standard and various other standards provide you the guidelines as how to perform the test and how to analyze the results, and it also provides some of the acceptance limits as well. Then we have another standard which is used very commonly by people out in the field when they are performing either acceptance testing or maintenance testing, and the standard is C57.152, which is IEEE Guide for Diagnostic Field Testing of Power Transformers, Regulators, and Reactors. So I highly recommend looking into these standards if you are a technician working out in the field performing different tests, and also getting an idea as what are the acceptance criteria. The IEEE C57.152 standard has a diagnostic chart which tells you what are the tests that you should perform if you want to check a certain component of a transformer. Since our focus is on the windings, this slide gives you information as what all tests you can perform to check the condition of the winding, and as you can see that it lists the ratio as well as the winding resistance test. Likewise, for tap changers, either it could be a offload tap changer, which people also call as de-energized tap changer, DETC, or the onload tap changer. For both of them, turns ratio and winding resistance tests are recommended, and as you can see that those are listed in this one as well. If we go outside the IEEE world, there are some other standards. NETA has ATS and MTS standards, acceptance testing standard and maintenance testing standard. And in both of those standards as well, for dry type as well as liquid filled transformer, it is recommended to perform the turns ratio test at the designated tap positions. And the acceptance criteria is that it should not deviate more than 0.5% from either the adjacent tap position or the calculated ratio from the nameplate. One of the exception is that if you run into small dry type transformer that are rated below 600 volt and below 500 kVA, the TTR test is optional. Likewise, for the winding resistance, this test is also recommended in the standard, both ATS and MTS. And the criteria for analyzing the reading is that if you see any deviation of more than 50% from the lowest value, either between the phases or similar transformers, it is recommended to investigate those results. Now that we have talked about various different standards that recommend these two tests for winding assessment, let's go into detail as what are these tests, how it is performed, what are some of the best practices, what are the things that a technician should be aware of when performing these tests out in the field. Transformer turns ratio test. Why do I need to do this test? What value do I get out of this test? As you know that this test is performed at various different stages of the life cycle of a transformer. If you are performing a acceptance or a commissioning test, the purpose of this test is to make sure that the windings are designed as per the specifications. You also want to make sure that it was designed accurately, as well as the verifying the quality of the manufacturing process, which includes to make sure that the turns ratio is correct, polarity is correct, the connections and the leads coming from the main winding to the regulating winding for the tap changers, those have been done correctly. So those are the things you can verify with turns ratio test. And as the transformer is in service and you perform your maintenance test or troubleshooting test, in those kind of testing, the goal is that you want to find out if there is anything wrong with the windings, that could be shorted turns or problem with the tap changer, that could be misalignment of the contacts, or other problems such as coking, or the contacts not working as intended when you switch from one tap position to the other. When we talk about turns ratio testing, the information that is available on the nameplate is very critical. You need to understand what is on the nameplate, how to input that information in your test instrument, so that when you perform the test, you get the result and you're able to analyze the results. So we're going to look a little bit into the nameplate information and make sure that we use that information correctly when performing the turns ratio test. On any nameplate, you should have the vector configuration of the transformer. I have an example here in this slide where the primary is a delta, the secondary is a Y connection with access to the neutral terminal. So that would become a DYN transformer. I also can see that the primary side is a 138 kV. The low side is 36.2 kV, which are line-to-line voltages. And because the Y side it's a Y connection, so it is listing both line-to-line voltage as well as line-to-neutral voltage. One thing that we need to understand is that when you perform the ratio test, you are testing A phase of the primary side to the A phase of the secondary side. And that's what you're going to get when you perform the turns ratio measurement. And mostly on the nameplate, the values are defined in line-to-line values. So we need to understand the difference between the two. In addition to that, I can see that the high side has a de-energized tap changer. It has 5 taps on it, and the nominal is the tap position C, which would give me 138 kV, and I can get different tap position based upon how the windings are connected internally, and as you can see that it has a different connection on the right-hand side column. In North America, it's very common to have a de-energized tap changer on the high side or primary side and on-load tap changer on the secondary side. You can run into different designs of on-load tap changer. The example that I have right here, you can see that I have a regulating winding that would get connected in series with the main winding, and as you can see that it has 16 tap position and a reversing switch. And what that would do is that with the 16 tap position and the reversing switch, I can obtain 33 tap positions. And those are the 33 tap positions you see on the nameplate. In some other cases, you might run into reactive type tap changers. And in those ones, in addition to the reversing switch, you also have a preventive auto. And the advantage of having a preventive auto is that you can operate the tap changer in the bridging position as well as non-bridging position, as you can see in the pictures here. So with this kind of configuration, I can get out of 8 tap positions, I can get 33 tap positions, because if you consider bridging and non-bridging position, and if you add a reversing switch to that, you can get 33 tap positions out of this tap changer configuration. So you have to understand what is on the nameplate, and based upon that, you would perform your test and make sure that the ratios are coming out right for different tap positions. As I mentioned, that the vector configuration is very important. If I pick a wrong vector diagram in my software on the test instrument, my results won't be accurate. I would have hard time determining the percentage error, because it would calculate wrong ratio. So let's talk about vector configuration. One thing to keep in mind is that any two vectors that are in the same plane or parallel to each other correspond to the same phase. For example, in this one, the H1, H3 and X2, X1 vectors correspond to A phase, and they both are parallel to each other. And when I do the test, I'm going to be applying a voltage on the primary side, which would be H1, H3, and then I should be measuring the voltage across X2, X1, which is the corresponding A phase on the secondary side. Now, when you look at the nameplate, you would see a delta or a Y connection either on the primary and the secondary side. And as I mentioned earlier, it would be called as a DYN because delta is on primary, Y is on secondary with accessible neutral. But then you also see something like DYN1 or DYN5. So the last number corresponds to the phase angle difference between the primary and the secondary line-to-line values. And the way to find out that phase angle difference is that you pass on a vector crossing the H1 and then you pass on a vector crossing the X1 terminal. And then you measure the angle starting from H1 vector going towards X1 in clockwise direction. And if it is 30 degrees, it would be written as DYN1. If it is 150 degrees, it would be written as DYN5. So every number increment is an indication of 30-degree phase angle. So this would be a good example. I can see that my primary is a delta, secondary is a Y with accessible neutral. But if I want to find out if this is a DYN1 or a DYN5, what I would do is that I would draw a vector going from center point through the H1 terminal. Then I would do the same thing going from center passing through the X1 vector. And then I want to find out the angle between the two vectors going in the clockwise direction. And it would look something like this. And this angle equates to 210 degrees, which makes it DYN7. So, as I said, it is very important to pick the right vector configuration. So you would look at the nameplate, enter the correct values of the voltages, as well as pick the right vector diagram before you start your turns ratio test. Now, when we talk about standard, the definition of a ratio test is that it's the ratio of the number of turns in the high voltage winding to that in the low voltage winding. In addition to your turns ratio test, you also measure the phase angle relation between the primary and the secondary winding, and through that you can determine if the polarity is correct or incorrect. Then we have another standard, which is the field testing guide for transformer IEEE C57.152. It mentions that the definition for turns ratio is still the same, but it also defines what we call as voltage ratio. So the voltage ratio of a transformer is the ratio of the RMS voltage of a high voltage winding to a RMS voltage of a low voltage winding. You may have heard this thing that I have a turns ratio tester. The interesting thing is that any of those testers out there, they do not measure the turns ratio. They measure the voltage ratio, and it is assumed that under no load condition, the voltage ratio is the same as the turns ratio. The principle of operation is that you apply a small amount of voltage on the high side, and that would induce a voltage on the low voltage side, and the two voltages are accurately measured, and the ratio of those two is defined as the voltage ratio. And as I mentioned, that under no load condition, the assumption is made that that would be equal to your turns ratio. So your turns ratio formula is your ratio of your primary voltage to the secondary voltage, primary applied voltage to the secondary measured voltage, and that would be equal to the ratio of primary turns to the secondary turns. And as I was mentioning, that the no load voltage ratio is approximately equal to the turns ratio. As we will go into the future slides, you will notice that by default, people usually apply the voltage on the primary side, but you can also apply the voltage on the secondary side of the transformer, and then it would act as a step-up transformer because most of the transformers are step down, but if you energize on the secondary side, it would act as a step-up transformer. Whichever winding you apply voltage to, the current measured during that time is called as the excitation current. So let's talk about some of the different definitions you might run into, because that is good to know, because you would be using those terms when you're going to perform the turns ratio test. So the first one is the transformer nameplate voltage. It's the line-to-line voltage that is defined on the transformer nameplate. That's what the transformer nameplate voltage is. The other term you might run into is called as the transformer nameplate ratio. It's the ratio between the line-to-line voltage of a high voltage winding to the line-to-line voltage of a low voltage winding. I want to stress on this thing that the transformer nameplate ratio looks at the line-to-line values. Then we have another thing which is transformer voltage ratio. It's the ratio between a specific terminal voltage of a high voltage winding to a specific terminal voltage of a low voltage winding. And this is typically looking at the phase values or a one winding voltage to the other winding voltage. Then we have our turns ratio, which is the physical number of turns on the primary side to the physical number of turns on the secondary side. And the last one that we have, which we call as the measured voltage ratio. You apply a small amount of voltage on one side, which could be the high side. You measure that voltage. It would induce a voltage on the secondary side, and that is called as the ratio of those two voltages. That's your measured voltage ratio. Now, why am I talking about all these things? Because when you're going to perform the turns ratio test, you would realize that these terms would come handy when you're going to look at the results. This is very basic. We know that for a delta winding, your phase voltage and your line-to-line voltage is the same. But for a wire winding, your line-to-line voltage is √3 times the phase voltage. Now, going back to the same nameplate information, I have a high voltage winding, I have a low voltage winding. Now let's look at those four terms that we talked about. Your transformer nameplate ratio would be the ratio of line-to-line quantities. So it would be ratio of 138 kV to 36.2 kV. Whereas the TVR, which is transformer voltage ratio, is a ratio of phase quantities, which is 138 kV of the delta side to the phase value of the Y side, which is 20.9 kV. So when I'm trying to do a measured voltage ratio, my goal is to compare that with the TVR. I'm going to repeat that again because this is the important part. You perform your measured voltage ratio and you compare that with the TVR, which is transformer voltage ratio. Now, on the nameplate, what is available to you is what we call as transformer nameplate ratio. You want to be able to convert the transformer nameplate ratio to transformer voltage ratio. And this is the table that is being used by most of the automated test set, where when you enter the nameplate information in the vector diagram, based upon that, it applies a multiplying factor to the transformer nameplate ratio, and from there you get your transformer voltage ratio, and that transformer voltage ratio is compared with the measured voltage ratio to give you the percentage error. Back in the days when we had completely manual transformer turns ratio meters, they would work on the principle of null detection technique. What you would have is that you would have a hand cranked voltage generator where you would use that to induce a voltage. that voltage would get applied to the transformer under test secondary side, and you would also apply the same voltage to a reference tab transformer. As you can see that this voltage that is being generated gets applied to the secondary side of the reference transformer and the secondary side of the transformer under test. And then using a null detection technique, which is connected on the primary side of both of those transformers, you try to find the null detection technique, and when there is no flow of the current, then the turns ratio of the reference transformer would be equal to the turns ratio of the transformer under test. This instrument was used successfully for a many number of years, and the advantage of using that instrument is that it would provide a highly accurate ratio, and if there is any shorted turns in the winding, you would be able to detect that when you would hand crank the turns ratio meter. So those were some of the advantages of the unit. But then because this was a single phase unit, you would have to move the leads around. It was a purely manual test where you would have to change the dials to get the null detection. So it was time consuming. It was relying upon the operator knowledge to correctly use the instrument. And because you were applying the voltage on the secondary side, you would develop high potential on the primary side. So those were some of the limitations of the unit. And as we moved along, and when we had better technology available back in the 90s, people started developing instruments that would apply the voltage on the primary side, and you would measure the induced voltage on the secondary side. And in addition to that, you would measure the polarity, you would measure the phase angle, and you would have all the leads connected to all the phases of the transformer, but you would have to manually switch from one lead terminal to the other one. So there was still some manual work that need to be done to perform the test with these kind of instruments available back in the 90s. Then we talk about today's instrument where everything is automated, and when I say everything is automated, you enter the nameplate information and then it would do the test on all the three phases, one phase at a time. It would calculate the measured voltage ratio. It would calculate the transformer voltage ratio, compare it with the measured voltage ratio, give you the percentage error, compare it with the IEEE standards, and give you the pass-fail criteria. Everything is done through computer, so that way at the end of the test or the completion of the test, you have a test report that is giving you a clear indication of the condition of the winding. As I mentioned, that most of the modern three-phase ratio test units perform test one phase at a time and then do the automatic switching. And because everything is automated, you enter the nameplate information, it makes the testing go really smooth and fast and efficient. So this is how you would connect the leads. As you can see that there are total 8 leads coming out of the test instrument, and those would go to the primary and the secondary bushings. And then you perform the test on all the possible tap combinations of the de-energized tap changer as well as the on-load tap changer. This is a sample result. As you can see that you enter all your nameplate information, your vector diagram, your voltages, and then based upon the parameters entered in the nameplate information, it would calculate the turns ratio or the voltage ratio. It would perform the test, measure the actual ratio, do the comparison, give you the percentage error, and that percentage error should be below 0.5% as indicated by different standards. One other thing that you would notice is that when you enter the nameplate information, the instrument would be smart enough to know which one is A phase, which one is the A phase on the secondary side, and likewise for the B and C phase. If you have a on-load tap changer, you would typically perform the test on all the tap positions, and this is how the sample results would look like, where you can see that all the taps were tested, and in addition to that, you have the percentage error column and the phase angle column, which would tell you that if the angle is less than or close to 0 degrees, that's an indication of correct polarity. Now let's talk about something that we all run into, but we either take it for granted or we don't pay that close attention to that. A lot of time what you would run into is that you would perform a turns ratio test, but depending upon what test voltage you're using, you might get different results. So if I apply a 40 volt, then 80 volt, and then 100 volt, and then 250 volt, I might get different turns ratios. That is what we call as voltage dependency when you perform the turns ratio measurement. That can happen because of number of reasons. One of the reasons could be that if you're testing a 3-winding transformer and the tertiary winding, the delta tertiary winding is kind of derated winding which has lower MVA rating, or you can have transformer that has poor magnetic coupling. That can be one of the reasons. Or one of the very common reasons that we run into is that when you're testing a configuration such as Y delta or a delta Y, in those cases, because of the delta configuration, if you're testing one phase at a time, for example, if I'm testing H2HO with respect to Y2, Y3, you can see that I apply the voltage on the primary side. I'm trying to measure the induced voltage on the secondary side, but the two untested windings act as a load on this winding, and that can affect my results. So we will see some case examples, and that would give you some idea. So if you do ever run into those kind of problems, there are a number of things that you can try that would help you improve your results. One is that you can apply 3-phase voltage where you're testing all 3 phases at the same time. I do understand that sometime a 3-phase source may not be available, but that is one option you can try. If you don't have a 3-phase source available, then you can test face-to-face testing where you would energize 2 windings at the same time. Or what you can do is that you can try to apply the voltage on the secondary side and make transformer act as a step-up transformer, and make sure that when you do that, the instrument is capable of doing that. As I showed, that the hand crank turns ratio tester would be an ideal candidate for this one if you were to test it from the secondary side. The other thing that you can try is that try to energize the winding that is closest to the core. We know that for a 2-winding transformer, the low voltage winding is closest to the core, and then on top of that you have a high voltage winding. So try to energize the winding that is closest to the core. So here I have some example that would give you a good idea as what's going on and what you can do about it. So I have a transformer which is a 3-winding transformer. The primary is Y, the secondary is delta, and the tertiary is a Y connection. And I'm trying to do the test between primary and the secondary. As you can see that the first set of result is your standard testing phase by phase, 1 phase at a time, doing the testing from phase to neutral. If I apply 8 volt, you can see that I'm getting a ratio which is outside the tolerance. Then I increase the voltage to 40 volt, I get better results, but I am still out of tolerance. Then I try a phase-to-phase voltage, the same voltages, and you can see that at 40 volt, my values are within the tolerances. The same transformer, if I were to use a 8 volt test voltage but try to do the test from the secondary side, same exact transformer, you would notice that my error is well within that 0.5% criteria. So there are different things you can try. If you ever run into a transformer that is voltage dependent, you can either apply phase-to-phase voltage, try to energize the secondary winding, or try to energize the winding that is closest to the core. So when we talk about the results interpretation, the criteria is 0.5%. From the nameplate value, the measured ratio should not deviate more than 0.5%. You would run into cases where the outer leg phases, which is typically A and C phases, they may read slightly higher error than the center phase, but as long as it's within the 0.5% tolerance, that should not be a cause of concern. One other thing I want to highlight is that when you are testing a on-load tap changer on the low voltage side, sometimes you may not have equal number of turns per tap, which means that when you are trying to test the intermediate taps, there might be a different voltage variation, and because of that, your percentage error may exceed 0.5% on the internal taps. But as long as the A, B, and C phase on any given tap are reading very close to each other, and the extreme taps are within 0.5% tolerance, you can accept the transformer and tap changer. It is okay. Those results are acceptable as long as the extreme taps are within tolerance and the intermediate taps phases are very close to each other. To summarize, TTR is a very common test. You need to be careful about the vector configuration and your nameplate information. The reason why this test is a preferred test is that it's an on-spot diagnosis where you can compare the results with the nameplate data. It is recommended to test all the taps of the DETC and LTC. If it's a maintenance test, then typically people test the in-service tap of the de-energized tap changer. Your three-phase transformers are typically tested one phase at a time, and then they do the automated switching to B and C phase. If you ever run into a voltage dependency where the percentage error may exceed 0.5%, it is recommended to try different things which we just discussed. Now let's talk about winding resistance. It is another test that is used to check the condition of the windings. Typically, winding resistance test is performed to evaluate and find out if there are any short-circuited turns, any kind of loose connection, if there is any problem with the tap changer, high contact resistance, also to verify that the on-load tap changer should make the circuit before breaking the circuit. So you can check the make before break operation as well. And then there are some other applications of winding resistance where you can measure the I square R losses, and you can also find out the internal winding temperature by performing this winding resistance test, and that's what we call as a heat run method. So what is this test? You are trying to measure the resistance of the primary winding and the resistance of the secondary winding. It's a DC test where you apply a DC current and you measure the voltage drop across the winding, and ratio of your voltage to current gives you the resistance of the winding. So this is how it looks like. You have a winding, you would apply a current, a DC current to it, and you would measure the voltage drop across the winding. Having said that, because it's a winding, it would have a resistance and it would have an inductance. And because it has inductance, the equation for voltage looks like this one. And when I look at this equation, I cannot do just V over I because I have one component which is called as L di over dt. I have to get rid of this component before I can do V over I. And as you can see the term L di over dt, which means that one of the component is rate of change of current. If I can somehow stabilize the current, which means that current is not changing with time, which means di by dt becomes 0, and if I can make di by dt over 0, that term would disappear, and then I can do the ratio of V over I. So one of the most important information that we need to understand for winding resistance is that the current has to stabilize before I can get reliable measurement. So my current has to be constant, it should not fluctuate. If it's fluctuating, you will not get reliable and consistent resistance measurement. So what do I need to do to get stable current in my winding? Well, it's a two-step process. The first one is that you need to saturate the core of the transformer. And in order for you to saturate the core of the transformer, you need to have enough flux in the core. And flux is defined as voltage times second, which means that I need to apply enough voltage for enough amount of time to develop enough flux to saturate the core. And then the second step is that once the core is saturated, then I can stabilize the current, and once the current is stable, I can get stable resistance measurement. Keep in mind that if your winding is bigger, or if it's rated for high voltage and high MVA, if the winding inductance is high, it will take longer time for you to get a reliable measurement because inductance would oppose the change of current. So to kind of reiterate, you need two things to make this winding resistance work. You need to have enough open circuit voltage to set up enough amount of flux, and then you need to have enough current so that it can stabilize. So when you are picking any instrument, make sure that you just don't pay attention only to the amount of current that it can give you. Also look at the open circuit voltage, because that is the part that would saturate the core of the transformer. When it comes to picking up the right amount of current, you can pick any current in the range of 1 to 15%. You may want not to exceed 15% because that's the upper limit recommended by IEEE standard, and minimum you would like to have at least 1% of the rated current so that you can get stable readings. Make sure that, as I said, make sure that you do not apply too much of current. More is better. That statement does not apply to winding resistance, because if you apply too much of current, you might magnetize the transformer core to higher levels, and then it would have some residual flux in it, and because of that residual flux, it may affect some other electrical tests that you might perform. And also, if you apply too much of current, you may heat up the winding, and when you heat up the winding, the temperature changes, and when the temperature changes, the resistance of the winding would change. So it is recommended not to exceed 15%. This is how the winding resistance works in the background. The current would start, it would be kind of non-linear, and it would stabilize, and the resistance would be fluctuating all over the place, and once the current is stable, the resistance would stabilize as well. If you look at the hysteresis curve, it is recommended not to have small levels of current, because then you are operating in the nonlinear region and you may not get good reliable measurement. Your best bet would be to saturate the core of the transformer and then have enough current which would stabilize, and then you get your measurement. So try to operate in this region to get reliable measurements. Once again, to reiterate, bigger the winding, bigger the inductance, difficult time you would have to get stable measurement. The amount of time it takes to get stable reading is based upon the time constant, which is defined as L over R. If you have higher inductance, obviously the time constant would be higher and it would take more time. So once you perform the test, once you have got good readings, it is very important to discharge the specimen or discharge the winding, you know that inductor stores energy, which means that if I don't dissipate the energy and I go and take the leads off, that whole amount of energy is going to dissipate where the connection gets broken, and it can develop a lethal amount of voltage which could be dangerous to transformer or the person who is operating the leads. So it's highly recommended to discharge the energy stored in the winding before you take the leads off. And most of the automated test set does that automatically. At the end of the test, they would discharge the energy stored, so that way it is safe to take the leads off. And as I mentioned that you should discharge the energy stored in the inductor before you take the leads off, and that is very important from the safety point of view. Now let's talk about the efficiency. When you are trying to perform the test on A phase, B phase and C phase, you don't want to put double effort. What I mean by that is that there is only one single core in the transformer, which means that if you have magnetized the core when testing A phase, and when you go to B phase, don't try to magnetize the core in the other direction. That would be putting twice the effort. So in order for you to make sure that you do that, if I test my A phase winding from H1 to HO, then when I'm testing my B phase, I should be testing from 0 to 2. And when I do that, I'm trying to maintain the direction of flux in the same direction. So when you test the B phase, the amount of effort that would be needed to get stable reading on B phase would be a lot less if you test from 0 to 2, and likewise for C phase 0 to 3. If I have a delta winding, you can see that if I test A phase, the current would flow from 1 to 3, and then because I have two windings that are in kind of series, and that series combination is parallel to A phase, there would be a flow of current from H1, H2 to H2, H3, which means that I have already started working on B phase in the direction of 1 to 2. So when you test B phase, don't test 2 to 1, that would be putting twice the effort. So make sure that you test B phase from 1 to 2. And likewise C phase from 2 to 3, because that's the direction you started with, and you want to maintain the same direction of the current, and that would ensure that your flux is setting up in the same direction. Sometimes what might happen is that the low voltage winding would take a lot of time to stabilize, and in those kind of cases what you can do is that you can test two windings at the same time. So you would connect the A phase of the primary and A phase of the secondary together in series by connecting the polarity terminal to the non-polarity terminal. As you can see that I connected H2 to X1, and now the flow of the current would be top to bottom and then top to bottom. So I'm maintaining the same direction of the flow of current. So now these two windings are acting together to saturate the core of the transformer, and you will get your readings faster by doing this technique. So this is another example. You have a delta Y connection where you can see that the direction of the flow of the current is in the same direction for both the windings. And now I have H1, H3 and X1, XO, and I can get both the measurement at the same time. So if I have 6 windings, 3 on high side, 3 on low side, I only have to perform the test 3 times, because each test would give me 2 measurements. This is another example of a YY configuration. Now let's talk about some of the standard and what are the recommended limits. If you were to do the winding resistance test, then you can compare the readings between the phases, and the difference between the phases should not be more than 2%. That's from IEEE C 57.152. You can also compare your results with the original factory test or the commissioning test, and the results should not deviate more than 5%. I want to highlight this, that if you're trying to compare today's result with the factory result, make sure that you correct the readings to a common temperature, because the winding resistance is a temperature dependent test. So I want to compare apples to apples. If the factory test was recorded at 85 degrees C, you want to correct your today's reading to 85 degrees C as well. As I mentioned that the results are, or the winding resistance results are temperature dependent. So this is the formula you would use to correct the readings to any common temperature. It could be either 75 degrees C or 85 degrees C. You can see here that Rm is your measured resistance and Rs is the resistance at any desired temperature. It is also very important to pick the right material for the winding, because there is a different constant for copper as opposed to aluminum. See, this is a sample result where the readings were corrected to 85 degrees C, and most of these test sets would do that automatically. You don't have to manually do it. And I can also see the winding difference is less than 0.5%. This is how you would connect the leads. Again, you connect all the phases, and then the test set tests one phase at a time and automatically switch to the other phase. This is just a kind of a summary of what we talked about, that if you have a larger coil, a larger inductance, it will take longer time, and you may want to try a dual injection method to get readings faster. Let's talk about load tap changers. When you are testing winding, you also want to check the condition of the OLTC. You want to make sure that it's making the circuit before it breaks the circuit. I want to identify if there is any high contact resistance, any kind of coking, carbon deposit on the contacts, any misalignment in the contacts, or if the contacts are in good condition or not. In past, people used to use a battery and a bulb, and they would excise the tap changer, and if the bulb goes off throughout the change of the tap changer, that would be an indication that there would be a problem with the tap changer. But nowadays, with the automated test instrument, you can define your parameters as how sensitive you want the test to be, and you can do this test, which is make before break test, and you can find out that if the tap changer is transitioning properly from one tap to the other tap position. This is how the sample results look like. As you can see that it did the test for the A, B, and C phase. The winding difference is less than 0.5%, and then also it checked the transition of the taps from one tap to the other, and it passed because the current never got interrupted during the transition. If you have a preventive auto reactive type tap changer, this is how the graph would look like for a winding resistance, and as you can see that it looks like a V-shaped curve, and then you see a zigzag pattern, which is quite common for a bridging and non-bridging position. If you don't have see in this graph right here, I have a reversing switch, that's why I get a V curve. But if you don't have a reversing switch, you would see a linear kind of pattern going in the downward direction. Once I have completed all my tests, your TTR winding resistance, it is recommended to perform the demagnetization on the core of the transformer, because you don't want to have any kind of residual flux in the core, because that would affect your other electrical tests such as SFRA and excitation current, and it also might trip the transformer when you energize the transformer. So the recommended way of performing the demag is to use DC current in the positive and the negative direction, and reduce the magnitude of it as you go along, and then you bring the current level down close to milliamps, That way you are magnetizing the core in the forward and reverse direction, and basically you are kind of simulating a AC voltage wave shape, but this would be a kind of a square voltage wave shape with decreasing magnitude. Once you demagnetize the transformer, now the transformer is in a state where it has no residual flux, and that would help you to get good measurement for excitation current and the SFRA test. To summarize the winding resistance, it's a highly recommended test to pick up any winding issues. Between TTR and winding resistance, your winding resistance is more sensitive test because the tolerance limit is only 2% between the phases. The winding resistance can also be used to check the make before break operation of the OLTC. You can also make sure that your LTC is working fine as well as your main winding. Some of the things that you should be aware of, that any large winding would have higher inductance. That would mean that it would take longer time to saturate. So it's not uncommon for us to see 2 or 3 minutes of wait time on big transformers. Anytime you have a delta winding on the secondary side, it will take extra time to stabilize because of the delta winding configuration. Make sure that you discharge the specimen, discharge the energy stored in the inductor at the end of the test, so that way it's safe to take the leads off. And the last thing is that you should demagnetize the transformer once you have completed the winding resistance test, so that way there is no residual flux in the transformer. Let's talk about some of the Megger instruments. We have a 3-phase turns ratio tester. It is capable of performing the test on all the 3 phases, 1 phase at a time with automatic switching. It has the capability of comparing the results with the nameplate and providing the pass-fail criteria. The unit is capable of working in a high noisy environment in a EHV station. In addition to that, you can do a lot of number of different things like automatic vector detection, testing non-NC configurations, testing phase shifting transformers. So the unit is capable of doing a lot of different tests. You can also perform the magnetic balance test. The other advantage is that the same lead set can be used with the winding resistance test set. So the next one we have is our Megger transformer ohmmeter. It is a 3-phase winding resistance tester, testing 1 phase at a time and doing automatic switching. You can use the same leads for TTR and winding resistance. Because I connect all of my leads in one time, I get less trip up and down the ladder on the transformer, which means that it increases the safety. You avoid any kind of hazard going up and down the transformer. As I mentioned that it has total 8 leads coming out, 4 on the high side, 4 on the low side. It is capable of doing dual injection, which means that you can test 2 windings at the same time. It is capable of performing the automatic demagnetization, and you can also check the make before break operation of on-load tap changes. The third unit that we have in our portfolio is a combination of turns ratio and winding resistance together in one box. As you can see that this unit is a one-piece unit with TTR and winding resistance combined together into one box. It is half the size of the 2 units, and it's about 40% less weight of the 2 units. You only need 1 lead set, so that way you can do turns ratio and winding resistance from the same connections. There is one single test form that would do turns ratio and winding resistance. Obviously, this is also capable of doing built-in demag, and all the instruments that I've talked so far, all of those are PowerDB compatible, which means that you can run and operate the instrument through PowerDB. And the last instrument that we have in our portfolio is TRAX unit, which is Transformer and Substation Test System. It is a multifunctional test equipment. It is capable of performing TTR, winding resistance, power factor, excitation current, leakage reactance, all of those tests using this unit. You would need another additional box if you want to perform power factor testing. The advantage of this unit is that there is one single software that is capable of doing all those tests. It's a very user-friendly interface. It uses the state-of-the-art technology for it to perform all those tests. And as I mentioned, that one unit can perform all the tests. That gives you the advantage of learning one software and capable of doing all the possible tests on the transformer. So this kind of summarizes the winding condition assessment. We talked about two tests primarily, turns ratio and winding resistance. Those are two very commonly used tests out in the field. And this presentation, as Jamie mentioned, would be shared with you guys, and we would be happy to answer any of your questions. Once again, these two are very important tests, and these two tests are recommended in different standards as well. I guess that's all. Back to you, Jamie.
All right. Thank you, Dinesh. At this time, the presentation portion of the webinar is officially concluded. We will now take 30 minutes to answer as many of your questions as possible. So if you have any questions that you haven't submitted already, please go ahead and submit them now into the Q&A box on the right side of your screen. And we will try to answer as many of those as possible today. For those that are leaving, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate it if you could take a couple minutes to provide your feedback so we can continue to improve upon future webinars. On the survey, there's a field where you can also request a demo or quote on any Megger products if you have any questions at all. A copy of the presentation along with a link to the video recording of the webinar will be emailed to everyone within about 2 business days. And you can also view video recordings of previous webinars on our website at us.megger.com/webinars. You can also register for next month's webinar there. That title is going to be Understanding the Time Domain Reflectometer Traces for Cable Fault Location. That'll be on July 20th at 10 a.m. Central Standard Time. And presenting for that webinar will be Jason Sushak, our Megger Cable Application Engineer. And before we get started with your questions, we'd also like to make you aware of a few hands-on transformer training courses from AVO Training Institute. They have a few different courses, transformer maintenance and testing, advanced transformer maintenance and testing, and also power quality and harmonics. Feel free to visit avotraining.com and view their upcoming schedule for all those courses. They've been training for over 50 years and have some of the most knowledgeable and experienced instructors around. And now let's go ahead and get to some of your questions. First question is going to be for our panelist, Diego. During testing, should all tap positions be tested?
Good morning, everyone. One of the typical questions will be if I have to test all the taps or not. The first question that we need to ask really is, what kind of testing are you performing? Is this the commissioning testing? Is it factory acceptance testing? If that is the case and you're commissioning and you're doing the acceptance testing in the factory, then I would prefer to test every single tap available in my transformer. If you are doing an operation in the field, and let's say that you don't have an LTC, a low tap changer, but you have only a DETC, I would suggest you to first make the question to the operations owner and discuss if that DETC has been exercised before. If the unit had the DETC in one position for a long time and that DETC has not been exercised, I wouldn't recommend you to move that one. So you will test only on the operational position. Then on the LTC, what is mainly important for you is to test the positions where the LTC has been operated. If you have the time and you can look into all the positions, especially for your excitation current test, for your winding resistance test, it is better to have all the positions being tested.
All right, thank you, Diego. Next question is for Robert. can you please re-explain the vector angle determination slides? And part two of that is, what does the dotted line on the bottom left of the delta triangle vector represent? And that they were referring to slide 17. Pull that up.
Sure. Good morning, everyone. So once we go back to that, we'll start again on slide 17, then I'll have you advance through them. But basically, this dotted line here is your phase reference. So this is on the high side here, and it's your phase reference. And if we kind of go to the next slide, yeah, thank you. If we can go, starting right here, I'll go back one or two. So if you go here, once again, instead of the dotted line, now we're drawing this arrow through once again for the phase reference on the primary side. And what we're doing is we're looking at this, and then we're going to compare our second vector diagram. So remember, this is a dy transformer. And so when you see something, the D will be a capital D, meaning it's a delta on the primary side. And then it will be a lowercase y, meaning that it's a y on the secondary side. And then it'll also have a lowercase n, meaning there's an accessible neutral. And then what you'll see is a number. So it'll be dyn1 or dyn5 or dyn7. So what that number means is basically how many degrees from that vector going from that x0 to x1 leg there, how many degrees to that phase reference on the primary side. So in this case, it's 210 degrees, and that number is basically how many times 30-degree increments. So that's why you have dyn1, you get dyn5, dyn7, different ones like this. So now, so here you have delta, that's the D, and then you have the lowercase yn, meaning it's a y winding with a neutral on the secondary, and that 7 is basically 30 degrees times 7, or 210 degrees on there. And then one other thing, if you guys will go back one slide, I believe. I actually went right to this one, number 20, actually. So if you look here, and one thing we want to point out is these are actual vectors. So you need to make sure that you have not only the magnitude, but the direction in this case. So h1 to h3 is comparable to the vector x2 to x1. But if you actually took that and tried to say h1 to h3 is the same as x1 to x2, you'd be 180 degrees out of phase. So you have to make sure you're correct on these vectors as well. So go ahead and advance one more time. Or go ahead and go another one. We'll go to these examples here. So now you see on this one, once again, the top one is a D for delta, yn, and then it's 5 because now that reference from that x0 to x1 vector back to your origin vector on your primary side is 5 times 30 degrees or 150 degrees. And then, of course, we had the dy, okay, and then on the second one, it's actually now a yn d7, because now the y is on the primary side with an accessible neutral, and then we have a delta on the secondary. And so now your origin vector, that dotted line, is going from the x0 to h1, and then our reference is from the center of the secondary to that x1 lead. And that's how we get that phase rotation on that one as well. All right. Anything I missed from the panel?
Nope, they said that's good. All right, thank you. Next question is for Diego. If we have a transformer with an inductive LTC, do you recommend to make winding resistance in all the taps?
For a transformer with an inductive LTC, actually it's interesting to do the test one direction and the opposite direction. So I would suggest you to go all the windings, all the tap change positions, and back and forth. Actually, if you look at the way that the test set is fixed for this test, you will do typically phase A or the whatever coil you have selected, and you go one direction with your top changer, and then you go from the last position to the first position on the next phase, and then you go again forward or backward on the last phase. So it is better to see, and you can compare actually what is the response on each of the top positions. So yes.
Okay, thank you, Diego. Next question is for Dinesh. Recently, we were doing factory testing for a transformer with a tertiary winding rated for 35% of nameplate kVA. We observed similar voltage dependence as described here. Is this sort of voltage dependence expected for all transformers with a tertiary winding, or only those with tertiary ratings less than 20%?
That's a good question. Usually when we talk about voltage dependency, what you would see is that it also has a lot to do with the design of the transformer. That 20% or below what I mentioned is what we have observed when we test a number of different transformers out in the field at different OEMs, all that kind of thing. So one thing I want to mention is that voltage dependency does not mean that there is a problem with the transformer. All it means is that you need to use appropriate amount of voltage to get good readings. So if you ever run into those kind of cases, you may want to use a three-phase source, as I said, or apply the voltage phase to phase, or try to energize from the secondary winding, or if you have a source that can apply 1000 volt and your winding can take 1000 volt, you may want to try to do those kind of things. The question, coming back to the question, the 35% of nameplate kVA, as long as your tertiary winding is derated, there is a high probability that you may run into the voltage dependency. And if you run into those, refer to the slide that I mentioned, and you guys will be getting a copy of those. But I have seen that anytime there is a derating of the winding, you may see or run into voltage dependency. But again, as I mentioned earlier, that I want to point out that that does not necessarily mean that there is something wrong with the transformer. You just have to use enough amount of voltage to make it work.
Okay, thank you, Dinesh. Next question is for Diego. How do you safely demagnetize the transformer after winding resistance testing or winding resistance test if the test equipment used has no demag option?
Well, that is a very, very interesting question, because what people used to do a long time ago was to go and bring the truck close to the transformer and try to demagnetize, playing with the battery from the truck. But that is not the safe way to demagnetize it. It is strongly recommended that you guys have a piece of equipment, a device that will be able to demagnetize, changing magnitude and polarity of the DC voltage that is being applied to your transformer. So other than that, you cannot really see if the unit is properly discharged after any saturation procedure. Anytime you apply a DC voltage, you're creating some energy on the windings that you would like to discharge. You don't want to be the path for that discharge energy. So better to have the equipment, and there's some old suggestions on the battery side that I think that nowadays we have the technology, so let's use the technology available nowadays.
Okay, thank you, Diego. Next question is for Robert. Is it a good practice to compare values between factory values and field values, or between past test values, or between different phases?
So I guess I'll kind of answer this one in two parts. The first, we can mention the TTR test, where now you're getting your turns ratio, and you can compare that to the nameplate. And of course, if you have factory test values and commissioning values, you can compare to that. So that's one nice thing, is you have a direct comparison or on-the-spot comparison all the time with those nameplate values and everything. Winding resistance, that gets a little trickier, I would say, because now you can go ahead, and if you do have some factory values, you can compare to those, and if you do have some commissioning values, you can compare to those as well. but this test is very sensitive to temperature. So you want to make sure that you're accurately recording temperature and you're correcting for temperature in your results if you are going to compare them from a previous test to a field test. In the factory, they can do a very good temperature-controlled situation. In the field, we really don't have that luxury, I would say. So when you are first doing a test and you're in the field, the best thing, what I always do is I do a phase comparison to see if my A, B, and C phases are close to each other, because they should be relatively close and they should all be at the same temperature here, unless you're measuring one day and one another day or whatever. But most likely you're doing all three at the same time, so temperature will be taking it out. So it'd be good to do a phase-to-phase comparison with the winding resistance there. But if you're able to correct for temperature and everything, then you can always compare to previous results and factory results. Just make sure you're taking temperature into account.
Okay, thank you, Robert. Next question is for Dinesh. Can we use a Megger DLRO to do winding resistance test, and what are the limitations?
We run into this question, I guess, all the time. When we talk about Megger transformer ohm meter, the test set specifically designed for winding resistance, the difference that it has in addition to like your regular 10 amp or 50 amp current is that it has a discharge circuit inside the unit that is capable of dissipating the energy stored in the inductor or in the coil. Whereas DLRO does not have any discharge circuit, which means that yes, you can run the test, you might get the reading from the DLRO, good resistance reading, but when you're going to go and take the leads off, you might run into a safety concern where it has not been able to dissipate the energy. The energy is still inside the inductor, and when you take the leads off, you might run into a possible arcing situation because that energy is going to dissipate through that broken connection. So from Megger standpoint, we do not recommend using a DLRO 100 for measuring winding resistance on large transformers. We have seen some cases where people have been able to use DLRO on small dry type transformer, but I won't be able to give you a cutoff line saying that 500 kV and below you can use DLRO and above you should use a MTO or a transformer ohm meter. That would be very difficult because every transformer has its own design. So my recommendation would be to use a proper winding resistance instrument because DLRO does not have discharge circuitry built into it, just purely because of safety reasons.
Thank you, Dinesh. Next question is for Diego. Why is time allotment for core saturation so critical?
Okay, let's look from the physical point of view. The first thing you have to remember is that a transformer is mainly a big inductor with a very, very small resistance. And when you apply DC for any process of saturation or demagnetization, you are playing with a time constant, which is the relation between the inductive component and the resistive component of your transformer. So you cannot split those two apart. And that means that there is a time function, right, for you to see stability on your variation of current with respect to the variation of voltage. And flux is basically a direct relation to voltage. In this case, to saturate your transformer or to magnetize your transformer is a function of volts times seconds, right? That's your flux. So it's directly related to time. You don't need only the voltage, you also need the current, because the current will allow you to speed up the function. But like Dinesh was mentioning during his presentation, please do not exceed more than 15% of the rated current of the winding, because otherwise you can get into overheating of the copper or aluminum material that you have, and that will affect the resistivity of that specific winding. So yes, it is critical. It's directly related to the function that you're trying to operate here during winding resistance or demagnetization.
Thank you, Diego. Next question is for Robert. During a dynamic winding resistance test, what would happen if an open circuit were encountered during the test, and how would this affect the test set?
So, kind of going back to Dinesh's point about the DLRO and everything, this is once again kind of a safety issue here. And of course, if you had an open circuit during normal transformer operation, it'd be detrimental to the transformer and the tap changer there. But during testing, if you're using like our winding resistance test sets and like a dedicated winding resistance test set, it will take that energy, and if it does have a open circuit occur, it will take that energy and discharge it through the test set and discharge it to the ground, protecting both the test set and the test technician as well. So we're monitoring that, and if something does happen, it'll discharge it. And the other nice thing is this is actually one of the tests we do to verify that your LTC is working properly. We're making sure that whenever you're transitioning from one tap to the next, you're connecting and you're making a connection to that next tap before you break the connection from the previous tap. So you're doing this make before break connection, and then we give you a good indicator, like if you saw our test results, we give you a pass or fail if we do that make before break connection. But if you do have an occurrence where actually that break happens first and you have an open circuit, we will discharge that current, discharge all that energy through the test set, through ground. Both the test set and the test technician will be protected there as well.
All right, thank you, Robert. Next question is for Dinesh. In a YY transformer, what is the best practice? Test H1-H0 or H1-X1 and so on?
That's a very good question, and the reason, with the limited time we had, we were not able to go that in depth. But think about this one, that you have a Y winding, and I'm assuming you're talking about winding resistance. So if your Y connection, if your auto transformer and Y connection, you can either measure from H1 to H0, or you have the option doing H1 X1 and then X1 X0. So my recommendation is to perform both the test, H1 H0 resistance and H1 X1 resistance. And the reason why I'm saying that is that when you do the winding resistance, you're not only just measuring the resistance of the winding, you're also measuring the lead that is coming from the winding through the conductor and through the center conductor to the top of the bushing. So if you only do H1, H0, and if there is a problem with the X1 connection coming to the center conductor and then to the top of the X1 bushing, you would miss out on that information. So it is very important that you cover not only the winding but also the bushing terminal, the connection from the winding to the center conductor. You have to take care of those things as well. So my recommendation would be to perform both H1 H0 as well as H1 X1.
Thank you, Dinesh. Next question is for Diego. Is it necessary to demag the transformer after you do a winding resistance test? And what happens if you don't demag it?
Okay. Well, let's go back to the physics, right? When you are running a winding resistance test, basically you are giving an orientation to the magnetic domains of your transformer. By doing this, right, you're saturating the core. And when you have the core saturated, if you energize your transformer, what's going to happen is that you will have high inrush current. And you will generate especially odd harmonics here, especially you will have a big component of second harmonic that may trip your protection system. Okay? So if you demagnetize your transformer, of course, you will minimize to a very low number these remnant magnetization in the core. And one of the things that is critical as well is not just for the energization of the transformer, but also for any additional testing that you may carry out on the transformer. If you did a winding resistance test, and after the winding resistance test, you will do some AC testing like ratio, excitation current, your leakage reactors, whatever the AC test will be next. Especially for excitation current, you will see an influence of the remnant magnetization of the core on the results. So you would prefer to do the winding resistance at the end, and before energizing the transformer, demagnetize it. And if you did winding resistance first, you would like to demagnetize before you do any AC testing. Now, when you isolate your transformer, the normal procedure will be to open a circuit breaker, to open a vector switch, to open something to isolate your transformer, and do an offline test, which is your ratio test in this case. When that procedure is taken in place, you will have a little bit of a DC component going back to your transformer. So if you really want to start from zero the procedure of testing your transformer, avoiding any remnants of magnetization on it, you will demagnetize the transformer first, then you will do your AC testing, you will complete your procedure with the DC testing of winding resistance, you will demagnetize, and then you will energize the transformer again.
Thank you, Diego. Next question is for Dinesh. When testing auto transformers, what considerations should we have?
I will try to answer this in two parts. One is from TTR point of view. As we were talking about the voltage dependency, you would run into some voltage dependency because you have three windings, and the winding farthest away, which is the high voltage winding, from the core, the magnetic coupling might be different. So if you're doing turns ratio test, you might run into some voltage dependency. So keep an eye on that. In addition to that, you may have a tap changer on those auto transformers, and sometimes I've seen that. I will try to explain it a little bit in depth. So typically your tap changer has plus minus 10% voltage regulation. And if you think about 33 tap position, which would give you 5/8% for each tap, 5/8% of voltage regulation for each tap transition. But sometimes what you may have is that you may not have equal distribution of voltage between the taps. And then what would happen is that if you were to do the TTR test, you would fall outside of 0.5% tolerance. And as long as it is consistent on A, B, and C phase, you should be okay. Or as long as it matches the commissioning results or factory results, you should be okay. But keep an eye on those things. And your extreme tap position should not deviate more than 0.5%. So those are the things I would keep an eye on when I'm testing auto transformer. And if the auto transformer has a tertiary with a delta winding, I would be very careful when I'm doing primary to tertiary turns ratio. Now let's talk about the winding resistance. It goes back to the other question that was asked, that I would do H1 X1, and I would also do H1 HO to take into account all the bushing connections. When I'm doing the testing on the secondary side, which is delta winding, you would notice that it will take a lot of time to stabilize the winding because it's a delta winding first, and that too on the secondary side. Secondary delta windings are the biggest challenge. So make sure that you allot it enough amount of time to get a stable reading. If you want to be more proactive, you can connect primary and delta tertiary in series and do dual injection to speed up the process of core saturation. But those are the things that I would keep an eye on. Make sure that you give enough time for delta winding saturation, because delta winding on secondary side are kind of tricky. So, yeah.
Thank you, Dinesh. All right, I think we have time for one more question. Last one's going to be for Robert. Are the same principles from these tests applied to lower capacity transformers?
Yeah, so on this, in TTR, you can do on all of them, and I would say winding resistance as well. just always remember to be within that the proper 1 to 15% of the rated current when performing the test with the winding resistance. So as long as you follow those principles, you can apply both TTR and winding resistance to transformers of all sizes.
Robert, I would like to add one small point to that, and those are all valid points. One additional comment on that is that if you run into small size transformers, what you may run into is that your turns ratio wouldn't be a problem. But winding resistance, what would happen is that sometimes the resistance can be really small for the low voltage winding, and meeting that criteria of 2% within the phases or 5% from the nameplate, because you are trying to measure in like few hundred microohms or like very small value, and 2% of that could be just overtaken by the instrument accuracy. So in those kind of cases, you may want to have higher tolerance, or you may want to have a tolerance not in percentage but in absolute value. Because of such low numbers, we run into these questions from tech support point of view that they are testing small dry type transformers or small pad mount transformers, oil fill pad mount transformers, and they cannot pass the 2% criteria between the phases or 5% from the factory. In those cases, it's not that your transformer is bad or anything, it's just that 2% is too low of a resolution for any test instrument to give you that kind of accuracy.
Yes, thank you, Dinesh. And I'll add one more point on that too, is that also when you're getting to that lower resistance, your connections make a big difference as well. And so if you're using those grounding studs or not, the little plug-in connections, and you're hooking to one spot of it, or if you're up even like an inch or two higher on a different side, that could influence the resistance as well, because the resistance of that connection will add to it. But yeah, that was a good point. Thank you.
Robert, your point was very valid. You are correct that even changing the connection a little bit, that can affect your reading. So that's a very good, valid point.
All right. Thank you, guys. Looks like that's all we have time for today. We apologize if we didn't get to your question. We had probably about 100 questions, so unfortunately we'll have to answer some of those offline, and we'll have somebody contact you personally within the next couple of weeks, hopefully, and get those answered for you. I just want to thank you all again for attending. If you can please remember to fill out the survey, we'd really appreciate it. Just be aware that on the survey there is a field for requesting a quote or demo on any kind of mega equipment or any kind of questions that you have. And thank you all again, and have a great weekend.